All right, I'm going to go over linear programming today. What is linear programming? It's just a method for optimizing a target value under a set of constraints. When can you use it? You can use linear programming when you need to find the best combination of numbers towards an optimum. So some examples of optimums are when you're trying to maximize something, when you're trying to minimize something, or just optimize the best mix of numbers. So classically, I think where most people encounter linear programming is when they're learning more advanced Excel applications, specifically using Excel's add-on solver, but these days you can do it in other ways like use Python or something like that. Some examples that I'm going to use to kind of illustrate linear programming is the traveling salesman problem. It's a very classical problem. Then I'm going to do one about warehouse and store transportation, and then lastly I'm going to do one on worker scheduling. All right, the traveling salesman problem. The traveling salesman problem is a classic example to illustrate linear programming and how to use specifically Excel Solver to find the optimal solution to whatever you're trying to solve. And so situationally, what you have here is you have the salesman who's going from city to city making sales. And not only is he trying to minimize the total distance required to visit all 6 cities, but he's also under the constraint that whatever city he starts off in, he has to end in that city. So for example, if he started off in city 3 and he goes from city 3, 5, 4, 2, 6, whatever, if he ends in city 7, he has to go back to city 3 to make a full loop, all right? So that's his constraint on top of just in general trying to minimize the total distance. So in front of us to start us all off is this distance array, and all it is it's a measure of miles between cities. And so how to read this is if you're in city 3 and you go to city 3, you have 0 miles because you didn't go anywhere, right? If you're in city 4 and then you go to city 5, it's 32 miles. Likewise, if you were to go to city 5 to city 4, it is 32 miles. And so right off the bat, what you'll notice is that along the axis of cities hitting themselves in that 0 line, these are basically just reflections of one another. Like this half of the rectangle is essentially the same as this half, just reversed in mirror reflections of one another. And so from an information perspective, you really only need half this rectangle, but the reason why we need this whole array is for the functions to work. So another way to put it is it just exists for Excel. All right. So with that said, let's look at how we're going to solve the problem. So here I set up a table as well as some calculations to figure out like the total distance. And so these are the values that you're going to want to try to adjust and dictate what path you want to take from city to city. And whatever you select here on the bottom, it's going to look up in this distance array what the corresponding miles is going to be. And so the first one's always going to be 0 because you didn't go anywhere, right? But when you go to 1 to the next city, in this case it's 1 to 2, it should pull up 1 to 2, 34, in which case we see that it does. And the way it does that is by using an index array. It looks upon this distance array and it looks on these two values for its row and column positions to pull up the correct amount. Now, I'm not going to go into how indexing works. You can look that up on your own, but one thing to call out here is that everything is designed to make this situation work. So Excel, just as a call out, doesn't really know that these are cities. It doesn't know the context. It's just the way we set things up so happens so that when we put in the cities, it corresponds with the positioning on this table. And I'll just leave it at that. If it doesn't make sense, just look into it. But that's how we pull up the values. We're using an index array. And then once we have all the distances, we just sum it up. And then this will be our objective function right here. Try to get this number as small as possible. So we'll keep this up here as a reference as the number to beat. 192 could be the smallest number. We don't know. We're just going to have to shove it through Solver to figure out. And so this is where we're going to play around with the values. So once again, these are the values that we're going to try to adjust to make the distance smaller, because whenever you change the number, it should find you a different array. All right. Okay. And then this number will be static. I mean, technically static. It's always going to be the first one because there's nothing we do about this. This one has to be the first city. All right. So we're going to change these 7. And then we're going to try to minimize this number. All right. So with that, let's click Solver. If you don't have Solver, look up how to get it, but it should be, go here, press File, Options, add it as an add-on, and it should appear. So we're going to reset everything. All right. So what's the objective function? Once again, it's this distance. What are we trying to do? We are trying to do minimize. So we want to minimize this value. What are we going to adjust to get to this objective? We're going to change these 7 cells. What are the constraints? This is kind of like the art of how to use this. You can do things, you cannot do things, and it might not matter. It really kind of depends on how your brain works. But one simple way to just kind of get things started is you can try to do anything and just see how it works. And hopefully you have enough knowledge of the problem so that like when solver populates a number, you'll have a sense of whether or not you're way off. And if so, that's when you go and refine your constraints. So in our case, all we're going to do to solve this traveling salesman problem where we're trying to optimize his pathing is we're just going to say, hey, of these 7 numbers, just make sure that they're all different. Because technically, if you want to get a low number, you can just make this all the same city and it'll effectively be zeros across the board. All right. So by doing this, it forces it to choose different numbers. One other constraint that we can put is we can say, hey, no number greater than 7. But as soon as it picks a number greater than 7, it's going to error out, and the model's going to, or the method's going to know and back off. So we'll just leave it at this for now. This we leave checked because we don't want negative numbers. And then now we have to select a solving method. So solver has 3 solving methods. The easiest way to put it is simplex LP is for linear type of problems. So anywhere where the data scales linearly, you want to use this one. Anything else, which is typically the case, you want to use GRG and evolutionary. So there's a few ways to figure out like what this is. Here they have definitions, but it's not really helpful if you're not like super technical. But essentially GRG uses calculus as its method to figure out its local minima, and then evolutionary uses random search. So both have their strengths. One's not necessarily better than the other. Back in like 2000s when I learned about this, you would typically use nonlinear first because computers were not as strong. But these days everyone's computer should be able to do both, so that like you should just peek at both and see what better answer you can get. Another way to think of it is the way that GRG nonlinear works is, at least the math is, it essentially just kind of like looks for value and tries to keep going downhill in terms of the values that it comes up with when it randomly shuffles the numbers. And so it just keeps going downhill until it essentially finds a valley of values. So what that means is, say it does a bunch of numbers and finds 165, it'll keep going 165, 150, 143, and once it keeps shuffling and it goes like 143, 143, 143, 143, it'll just assume that that's the right number. Whereas with evolutionary, it's a little bit more robust, where it's kind of like throwing darts everywhere, and then whatever value it has, it will hold based off of your objective, and it'll keep replacing with a better value. So in our case, it's min. So what it's going to do is first it'll do a random value, and it might be 165, and it'll hold that value, and then it'll shuffle it again. And then if another value pops up that's lower than 165, it will replace it with that new number and keep going. So that's fundamentally how they both work. Like I said, in the past, evolutionary was slower, and it is slower today if you expand the options big enough. But on small problems, they're effectively pretty close. But when we run it in a second, you'll see the difference in timing, all right? So once again, just to emphasize, GRG nonlinear and evolutionary solvers work in totally different ways. They're not necessarily better than the other. It just kind of depends on what you're trying to solve and which model fits its strengths. So yeah, so we're gonna do GRG nonlinear. We're gonna go here. We'll just do 10 seconds, press OK, and we're gonna see what it solves here. Okay, so as you see here, it's set to be up here, and now Excel is gonna try to figure out the best combination in cities traveled to get you the lowest number. So we'll do that. Okay, so as you can see here, what it's found is if you start in city 1 and then go to city 4, then 2, then 5, and so on and so forth, and end in city 6, you should get a nice lower number, 163, okay? So let's do that a few more times to see if we can get a smaller number. So 163 is the number to beat. So let's go restore original values, press OK. So it's back to, was this the original value? I don't know. I wasn't paying attention. Oh, it was because I messed that up. So let's go back to here. Let's see what it finds again. So 163 I think was the number. Let's see what it finds now. 166. So let's go back. Okay, went back again. So 166. Let's solve it again. 166. Okay. So this time, let's try from this seed. See if we can find a smaller number from here. Okay. Or actually, you know what? Just to emphasize. So let's start from here again to emphasize the methodology. So I think if you start from here again, it should hit 166 again, but maybe not, because sometimes it just goes in a random direction. So it hits 166 again, but we know it can go smaller. So because it's always starting from the same origin, let's try to do it using this mismatch and see if we can find something smaller than 166. So go here, solve, 162, all right? So we did that. So let's see if we can find another one. So solve again, 162. Okay, solve again. It looks like 162 might be the smallest, right? And so there's that value, All right. So let's go back to here and let's put this back in. So 162 seems to be the best combo, and let's run this again. And if you see here, if you run from 1, 2, 3, 4, 5, 6, 7, it keeps hitting 166. And what this does is it illustrates the fact that for as fast as it is, one of the pitfalls of nonlinear is it can only find local minima, not the global minima. So what that means is, like I was saying before, is it just kind of keeps going downhill like from a math perspective until it hits a plateau. But that might not be the lowest plateau. Like, it might go down furthermore, but because it hits the plateau long enough, it just cuts it there and assumes it's the lowest number. And so that's one of the pitfalls of GRG nonlinear, is that it might be stuck at a local minima, but not the global. So that would be a case for why you actually want to use evolutionary then, because like I said before, it goes in a random direction, so it has a better chance at finding the local minima. But once again, it really depends on the options that you use and the problem itself. So we're going to do evolutionary, we're going to do solve. Let's even get higher than 166. So if you see down here, it's right now solving many thousands of different combinations, and it's already found one incumbent smaller, 159. And so I'm not going to keep going, but this kind of illustrates how the strength of both models, where by going in every direction and testing every single option, it was able to find a number much smaller than this. GRG linear may have found 159 eventually if you let it run for like a minute, but there's no guarantees. It's really just at the mercy of how they both kind of solve things. So that's how you use solver. That's how you do linear programming. To kind of like wrap it all up, essentially what our solver told us to do is the most optimal way to do this pathing problem is, as a salesman, you start in city 5, then you travel to city 3, 4, then you go to 2, 7, 6, 1, and then finally finish back in your origin city 5 to get a distance of 159 miles versus something like 192 miles. All right, on the off chance you watched my other video about the traveling sales problem, all this is kind of like a companion video to that. And what it is it's the same conditions, but I truncated it. Rather than 6 or 7 cities, it's only 4 to kind of illustrate what's going on behind the scenes, all right? And so in front of us, like before, you have a distance array here of the 4 cities. And what it is, so for example, from city 2 to 3, it's 12 miles. From 3 to 3, it's 0 miles because you're not going anywhere. It's just the distance between cities, right? And so the situation is, once again, the same thing. You are a salesman going from city to city, and you're trying to find the most optimal path sequentially from city to city on your sales route so that the total distance is minimized, while also under the constraint that the beginning and ending city has to be the same. And so before we get into the solving thing, one other thing that I've done differently here is I've listed out all the different combinations. Because there's only 4 cities, your total combinations is 4 times 3 times 2 times 1, 24. And we see here that it is indeed 24 different combinations. And I've also gone through the trouble of highlighting all the different combos to show that of the different combos, really there's only 3 outcomes you can find. A distance of 65, 86, and 103. 103 is the highest, 86 is the mid-level, and 65 is the shortest. So when we start to solve this, what we're going to try to shoot for is 65. And not only that, what we see here is that there are multiple ways to hit 65, so there's more than one answer. Okay, so now if you look at the solution table, same thing. Up here is going to be your inputs. Down here is your equations. It is similarly going to be using an index function to pull the correct distances between cities, and then this is just a summation function, and then this is lastly just an equal function to satisfy the constraint that the last city has to always be the first city. Okay, so what we're going to do here is we're going to highlight this. Right now, this reference path that we've arbitrarily chosen will give us an outcome of 86, and we look here, 86 is indeed an outcome, so it matches, and so we ideally want to go to 65 and never to 103. So we go here, we go to data, solve, we're going to reset everything, go here, solve. We want to minimize this, and we want to do it by changing these 4, and then we want to add the constraint that all of these have to always be different. Okay, and then the method is, this isn't a linear problem, so we have to choose either GRG nonlinear or evolutionary. Once again, it really depends on your knowledge of the problem. Because it's such a small problem, I think it's going to be neat to try both. Let's do GRG nonlinear. Once again, the methodology with GRG nonlinear is that it sort of travels along in terms of the math, the calculus. It travels in a downhill valley type of way. So what that means is it'll start with a number and it'll try to keep finding a smaller number. And once it starts calculating numbers of the same amounts or exactly the same, it'll just stop and say like, this must be the lowest one. The challenge with that is that by doing that, it sometimes only finds local low numbers and not the true lowest number in all the possible sets. So one way to illustrate that is if we were starting at a combination that gave us 103, there could be a chance just by random walk that it finds only 86. And once it hits 86 enough, it might say, this is probably the lowest number. Whereas if you chose the other method, because it goes in every single direction, it is more likely to find the true lowest number, 65, than the other methodology. But once again, like, it really depends on your problem and what's at stake here. So let's do GRG nonlinear and just solve and see what happens. So 86 is the number to beat. It found 65, so in our case it works. So we're going to restore this, and what we're going to do is we're going to try it the other way. We're going to try starting from 103. Okay, so we put it here, 103. So let's try. Let's see if we can find something better than 103. 65, that's good. Let's restore it. Let's try it again. 65. Let's try one more time. 65. Okay, so it works out. So in this case, this would be kind of a backwards way of saying that, you know what, we didn't have to choose the more advanced calculation method. GRG would have been just fine. But just for giggles, let us try running this to see if we can find the lowest number as well. So let's just pull any random combo. And so this is going to say if we start in city 4, went to city 1, 3, 2, and then finally in 4, we'll have total distance of 103. Let's see if we can beat that. All right, so we're going to go to solver. We're going to choose evolutionary, and we're going to solve. And what you notice down here is, the different combination was so small that it found it in a few thousand combos to be 65. In the previous video, you see it run a little bit more, but basically what it did was it went through in every single direction. Because it's such a small one, it hit all the combos, and it was easily able to pull 65. Using this method, it should never pull 86 or 103 unless your constraints are wrong. So yeah, hopefully this helps kind of better illustrate what we did in the previous video. All right, on to another problem, a supply and demand problem. So in this case, the fictional situation is we have 3 warehouses with a set amount of supply, a supply constraint, if you will. Then you have a bunch of demand nodes here, stores, if you will. And then lastly, you have on top of that different cost functions in supplying these different stores. So the cost for warehouse 1 to supply store 1 is different than the cost for warehouse 2 to supply store 1. And so all that can be seen here in the static conditions and constraints side that I created. And so if we go one by one and look at the elements, the first constraint is each store needs this many resources to exist, if you will, whatever that function may be. Each warehouse has only this much. If you sum the demand and supply up, you'll see that the demand or the supply exceeds demand. So we shouldn't have an issue with supplying all the stores and having them run. On top of that, like I said before, each shipping lane has a different cost function, which you see in this table. So once again, store 1 to get stuff from warehouse 1 is going to cost $3.50. From store 2 or warehouse 2, it's going to be $6, and then from warehouse 3, it's going to be $2.50. So there's going to be some optimal pathing to get supplies from certain warehouses over the other that we're going to have to try to figure out here in this problem. So on the right side is the problem set up, and so what I have here is the solution already pre-baked in. So let me clear that. So right now, as a placeholder, I've said that, okay, warehouse 1 is going to supply 1 to each store. If we look at it horizontally first, this is the total of I guess, supply going out of each warehouse. So for warehouse 1, in total, it gave out 4 supply, which is much less than its limit, 5,000, so it should be fine. If you look at it vertically, this is just the summation of how much resources the store has. So in this case, store 1 only has 3, 1 each from each warehouse. That's less than what we need, so that's not going to work, all right? So this is the setup though, like functionally though, it works. That's all we're testing here to make sure the math works, that the constraints match up. So once again, let's check. Store 2, the constraint should be 4125. It is. All right, that's good. And then likewise for warehouse 2, the constraint for supply should be 6,000. It is. We should be good. And then the cost function is very simple. It's just a sum product of what how the warehouses supply the stores and the cost. So behind the scene, how the sum product works is it'll look at the sell value. So in this case, let's just look at this one. warehouse 2 to store 2, it knows that it sent one thing over. So it will look at this array, it'll look at warehouse 2, store 2, and say like to ship it over, it's going to cost $5.50 per unit. I guess that's the other thing I didn't say. This is per unit, and then that's how it calculates. So it just multiplies all this by this for a total of 53, okay? And so onto the problem itself and what we're trying to optimize. What we're trying to optimize is to satisfy all these constraints. Primarily this one, really. Like if we have extra here, it doesn't matter as long as we don't exceed it. But satisfy this and try to get this number as low as possible. And so right now we're at 1111, so this is a really low number, but it doesn't satisfy this, so we know that it does not work. So with that said, let's get solver going. So let's go to data, let's go to solver. Let's reset everything to start from scratch. So what's the objective? It's going to be this value. What are we trying to do? We're trying to minimize the costs. What are we changing? We're going to change all these values. And then what are the constraints? This is your bread and butter. So the constraints are this total from each store has to be equal to this demand constraint right here. Okay, so we're going to press OK. Next, the total that shipped out of these warehouses must be less than or equal to their supply constraint. Okay, and then I think that should be fine. One thing what we can do is we can also just bound it. So depending on the solving method, it will check in a direction, but what might help like minimize the calculation time is putting a constraint on what values you can put here. So I'm going to just arbitrarily say that, like, okay, you can go with any number here to figure out what number, but let's just say like the other constraint should hold it to make this within the bounds. But what might cut out a lot of options that we don't need to check from the beginning is we can say something like, okay, well, I know that at any given point, you can't have 6,000 here, so I'm going to leave that as my upper constraint. Once again, this is like just some arbitrary value that has some logic to it. You can pick 3,000, 2,000. What I'm just doing is I'm just trying to like limit the number of combinations the solver is going to have to do to get to the number, all right? And so a little bit, so a little bit is an art, so you don't have to always agree with me. Sometimes it's trial and errors, but I'm just going to shove that in there just to see what happens. Then lastly, you have to just choose a solving method. So you have three types. Simplex LP is not appropriate here because this is not a linear problem, so it leaves these two. GRG nonlinear and evolutionary. If you haven't seen the other videos, basically they're just different methods. One is not necessarily better than the other per se. It just really depends on the situation. GRG is going to approach a minimum through calculus. The challenge is it might find only a local minimum. Evolutionary will go and will do a random walk to try to find the minimum. It will be more guaranteed to find the true minimum, but it might take too long. But these days with computers, we should be fine. So I'm going to first start with GRG nonlinear to see what we can get. So we do this, we go to options. The combinations probably are a little bit greater, so it's 4, 12. 4 times 3, so there's probably a lot of different combinations it's going to want to do. So I'm going to just do 15 seconds. We're going to press OK, and then we're going to solve and see what we can get. So this is the number that it got. We're going to press OK for now. And so I'm going to change this a little bit so it's easier to read. Oops. Okay, so one of the answers is this. So I'm going to do this. I'm going to just paste the value. Okay. I'm going to do GRG lin. Okay. That's one of the solutions. I'm going to use this as a reference point, and then what I'm going to do now is I'm going to reset everything, and let's just see if we can do this again. So go back to data, and let's just see what it gets. 3908, let's restore, let's try again. 3908 looks pretty promising. Let's try something else. Let's do 20 seconds here. Let's see if that helps. Solve. Still fine. I also didn't restore the original values. The original values were that, so let's try that again. Oops. Okay, solver. Let's try 20 seconds. Let's try 39018. Okay, so that roughly looks like it's small. One way to further enhance this is you can let it run longer, but it looks like it's solving before the 20-second mark, so it seems like it's pretty set on that value. So what we're going to do is we're going to reset it, and then we're going to now test the other way, evolutionary. So we're going to do this, solve, and let's see what it goes. See where it goes. So you see on the bottom, it went through a few iterations, 1,000, and in this case, it can only find 61,000. So the reason why it does that, and on top of that, what you'll notice is that it doesn't quite satisfy the constraints, so we can't quite use this. And part of the reason is because evolutionary solver doesn't respect true equals, and so in a way, you can actually could have assumed that you probably shouldn't use it for this type of this type of problem. And the reason why it only is returning 61 is because of the nature of how it solves things, because it's going through every single random probability, it just hasn't gone down to 39,000. So as an example, if I were to plug in this value here, this combination, it would have had a better chance to find it. But once again, because it goes in every random direction, it would still take time to find this. So one way to get closer to this value is you can ask it to run for much longer. You can ask it to run it for like, say 30 seconds, which I'm not going to do. Or you can change these conditions. You can change how exact it is. You can change its mutation rate. But once again, I'm not going to do it for this video just because of timing. And that would be ways that you can get it closer to 39 quicker. But just to iterate, the reason why it's only landing on 61 is because it's running out of time before it can find a much lower number. And one way, like I said, is you can seed it with something that's close, and it should be closer. But if you start from 1, it's just not going to get there. So here's what I'm going to do. I'm going to do this. I'm going to have it solve it by nonlinear, and it's going to get 39. Oh, no, I only got 55, so that's the local minima. So here's what we're going to do. So here's the double whammy. So the reason why GRG nonlinear is not finding 39,000 again is because it only finds local minimum values. It kind of operates on a peak and valley type of situation using the math. And so what's happening here is when it started with the other value, it started looking for lower and lower numbers, and it found 55. And then it started hitting 55,000 over and over again. So then it just made the assumption that, okay, this is the best we can do, and quit. When in reality, 39 is the much lower number. And the reason why it got there was because by doing 111 across the board, that was a better starting place for the math. So once again, if you let both methods run for a little bit longer, it could have probably got there. But in this case, it's not because of the reasons I just stated. So if I run this again using this, I wonder if we can get a lower number. There you go. See, it found 39. So it's really just arbitrary on like where it starts, and starts calculating before it can find that. And so likewise, because we start here, let's go back to GRG or evolutionary and see from this seed if we can find something smaller than 39,000. So if you see here, it's solving 1,000 problems. It's found something that's 38,000. So the number it found was 38,000, which is lower than 39. So this is an example of how evolutionary is probably the better method. But, well, no. This is a good example of how evolutionary found you the better answer for your problem. But once again, it also depends on the overall circumstance. So see here, it couldn't find the total constraint. So even though it found a cheaper way of supplying, it would still fail because it didn't find the exact constraint of like this has to equal. So in this case, really the answer is you have to use GRG nonlinear, solve it, and then if you see here its exact numbers, this would be the true answer. This would be the true answer of how you'd fulfill each store. There might be some different combo, but this is a good enough answer because it satisfies the constraints. All right, in this last example, I'm going to do a production scheduling problem to illustrate linear programming. Conceptually, what this idea is, you have a bunch of workers, you have a one week schedule, Monday through Friday, and you're just trying to figure out the optimal way to schedule them all while under some set constraints. In this case, you need to have at least 5 workers per day for the factory to run, and then you have to try to ideally produce a certain amount while minimizing the cost. And so that minimum amount is we need to at least make 30 per week of this widget, okay? And so let's start with some of the static conditions and constraints. On the left side, we have a table of workers that I made. You have the workers, you have the hourly rate that it costs for us to have them working. Then I create something called like this ability unit, and basically it's just some value that translates into one product. And then also for this column, I've added something called a worker tag, and it's mostly to try to give this some business context so that it's just not just numbers. So what I mean by that is I've arbitrarily created worker 2 to be a high performer. So what that means is not only among all the workers is he the highest paid, but he's also the most capable. Then you have someone like worker 7 who is the least capable if you sort this by ability unit, but also not the least paid, but he's someone who'd be considered a low performer. So maybe somebody who's been at the company for a while that just kind of like is coasting because he knows people. And then finally, we have someone like a rising star. And what that means is if you look at how much people make, even though he produces quite a lot. He doesn't make as much as the highest performer, so either he's getting there or he just started, right? And so these are just some tags to create like some profiles that kind of like make some business sense, so that whatever outcome the system comes up with, maybe it might track with what we would expect, okay? So once again, this is just a table of attributes for the workers to help dictate who should be working. Then we have the product quality, the product qualifications. And so to create one product, you need 15 ability units, I guess, on the floor. And then for each product, we can sell for $130. In order for the factory to operate, you need at least 5 people on the floor. And then ideally, management has dictated that every week we at least have an output of 30, okay? So those are our constraints. So then now let's get to the table itself to figure out the most optimal scheduling situation. So workers on the floor is simple. We just sum whoever's in that day. So we'll do that. We'll do here. And the max capacity has to be this. It has to be at least 5. So we'll do that. All right. The horizontal addition will just be hours worked for the individual. So in this case, I've arbitrarily set everyone to be 40. All right. So we just need a sum. Okay. We're going to just do sum this. And then we're going to multiply it by a theoretical 8 hours. So if we kind of read this out, if everyone worked every day, they'd be working 40 hours a week. Okay. So now and also we need to convert. So what this means is, so every day, so on Monday everyone works, and what it is it multiplies this. What this is looking is it's a combination of X lookups. And this is not as important, although for some people, if you want to try to reproduce it, could be. But conceptually, what it's doing is it's individually looking up each worker if they work, and if they work, it takes their ability unit, assuming this is a daily ability unit, and then it sums it all up. So conceptually, how that would kind of read is worker 1 in a given day can produce 30 units, 30 ability units, which roughly translates to 2 products, okay? That's kind of the way I structure the problem if you want to like conceptualize that. And so if in total everyone produces 305 ability units, all you have to do is do this, divide by 15 to get the output. So if everyone worked on this day, the output is going to be 20, okay? And then what we're going to do is we're going to lock this conversion rate here, and we're going to carry it over, and then we're just going to sum everything here. And I probably should have been better. I probably misspoke earlier, but the factory minimum output per week is 30. So if everyone works every day, we would meet that, but it would cost us 137, the net profit would only be 137. So that might be good, but maybe there's a better way where not everyone has to work, and we can still satisfy this condition and still make a better profit. And so what we're going to do here is we're going to paste this here as static values, as like a relative comparison, so that when we use Solver to figure out the best way of scheduling people, we'll have a sense of whether or not we're doing better or worse, okay? So with that said, let's do it. So let's go here. We don't have to select anything, so let's go to data, let's go to Solver. We're going to reset everything, okay? What is our objective function? Our objective is to maximize profit, so we want to do maximize. And profit here is just a function of just how much it costs for people to work minus the sales. How do you get those numbers? Total cost is just if they're working, it multiplies by their daily rate by 8, and then total sales is just however widgets you have sold by 130. So if we go here, it's this times this, and this is just a dirty combo of if they worked, they work by the hourly rate, and it should be multiplied by the hours also. So if you see here, it takes this, it takes how much they worked for the week, multiplied by their rate, and then it'll get you your total cost for that week. And then if you expand it out to 1 year, this is where you kind of see the value of optimizing your scheduling, because if everyone were to work, which could be the optimal, in a given year, you'd only make 7,000 profit. And there might be just some better value out there. So we're actually going to paste this here as well, just as a reference point. And then now let's go back to Solver. So we're going to do that. And now let's put in some of the constraints, okay? So one of the constraints is for all these variables, it can only be on or off. Oops, what did I just do? It can only be on or, what the heck? Oh, it's dumb. it inputted the variable. So the objective is going to be this one, change variable cell is going to be this one. The constraints are going to be, so for all these constraints, it's either on or off. So in this case, it's going to be a, I'm blanking, integer or difference? No, it's integer. No, it's binary. Or bin is binary, so it's this one, binary. So what that means is the only values you can use to put here is either 1 or 0, which translates to they're working or not. Okay, so that's 1. The other constraint is this has to be at least greater than or equal to this constraint, workers on the floor, because it needs to be at least 5 per day. Then we're going to add this. The amount of hours that these workers are working can never exceed the hours available. Right there. Okay. And is there any other constraint? Oh, this one. And then the total produced in a week must be greater than or equal to this guy right here, factory minimum output there. So these 4 should set it. And then now we just need to pick a solving method. And so if you see my other videos, there really is no guaranteed difference between, or guaranteed benefit between these two. You just have to have a good sense of the problem and kind of know what you're working with and sense of local minimums and stuff. And so one thing that we can do here is, because computers are smart enough or strong enough now, back then, the early 2000s, you really had to think about it because sometimes it would take too long for evolutionary to come up with the solution. But these days, they're strong enough to do it. So we'll do both. But because evolutionary solving method is really not good about constraints, sometimes it'll just get close. Oh, actually, that's not true. It's only bad with true equals. This is just roughly like underneath or equal, so it should be fine. So what we're going to do is we're just going to test both ways. So in this case, we're going to, because the outcome is nonlinear type of problems are like if and statements, min max, or binary switches. We're going to do GRG nonlinear first. We're going to set it to 15 seconds. Okay. And then we're just going to run it and see what we can get. So if we see here, we're going to press 1620 is the first guess that it made. Let's restore it and let's just try again to see if we can get something better. So 1620 is the number to beat. Let's see if we can get anything better. 1620. Let's try again. 1620 is the same thing. Okay, so it couldn't find it. So let's kind of look at the results. So did it meet all the conditions? It should. Okay, so essentially what it said was, of all the people that you gave me and all the different rates and ability, we've decided ultimately that it's best to work these 3 workers. Don't work worker 4. Don't work 6, 7, 8, and that's it. And to a certain degree, it makes sense for 7 because we should expect that because he's a low performer and he's expensive. So going into this, we ideally think that they either we use him very rarely or never, which this matches. And then conversely, the highest performer is probably also someone that could be used very sparingly, but you probably still want him on the floor at some point. And then this guy should always be on the floor because not only does he produce a lot, he's cheaper. So conceptually, this seems to all make sense. And so this is one possible answer. But once again, one of the challenges with these things is that you might accidentally find only a local minima. So you're going to have to keep running it to see if you can get a better number than this. So let's also take the time to digest what we see here. So based on this structure, you make $1,600 a week in profit. If you expand that, it's $84,000. So the difference is the difference in optimizing your scheduling is a profit of $77,000 per year. So this is kind of the real world benefit of using things like this to optimize problems that you might have in the real world. So before, if you just blindly worked everyone every day and didn't think about it, you would only be making $7,000. If you're smart about it, it'd be $84,000. So once again, this is a number that people will pay attention to. So this is the number to try to beat. What we're going to do here is let's just take this value and let's just paste it down here. And we're just going to use this. So GRG linear. Let's just play around. Let's just see what else we can get. So from this starting point, I'm going to so one of the challenges with GRG is it follows the same thing. So sometimes you have to seed it with different values to try to get it to run and maybe coax it to try to find a different minima. So we're going to just put some random values and see if we can find something better. 1600. Okay, so in this case, it's the same thing. So that didn't work out. So let's try, in this case, evolutionary. So let's solve. Let's solve. And you see down here what it's doing is it's going through thousands of different combinations. Right now, the lowest value it's found is 1600, so that might be the answer for this problem. And so 1620 is the lowest you can find, so this could be the answer. So what we're going to do is we're actually going to press OK, and we're going to give linear solver another chance. We're going to set this all to 0, or evolutionary solver, and let's see what evolutionary finds again. So starting with 1000, see, it found a much lower, or oh, I forgot, we're going for higher. It found a lower number so far. So it's gone through 7,000 combinations. Still can't find anything better than 1620. See, it's stuck here now. Oh, never mind. It's because it's done. Okay, so let's press OK. So it looks like 1620 might be the answer here. I'm going to try one other thing. So sometimes you need to coax it with the right seed. So what we're going to do is we're going to try to get this to a higher number. Oh, but then I don't really know how to, if I press 1 here, will it go higher? No, it goes lower. We're kind of just guessing in the dark now. I'm just going to put a random seed here. I'm going to put random things here. Let's try again with evolutionary, see what it gets us. Still stuck on 1620 as the highest value you could find. It's going through 5,000 different alternatives, 7,000 now, 8,000, still can't beat 16. So 1600 is most likely a real combination. And so let's see here if it did anything different. So in this case, similarly, it worked your top stud, it worked your up and coming. In this case, it's kind of weird. It actually chose to bring your worst performer. And then what did it do at its expense? It made 3 people work less. Huh, 16, 1240. Oh, I know why. It's because when I click solver, I reverted back to the original values. If you do this again, it's going to come up with the right number, 1620 as the max value. This was the, to reiterate, this was the values that I randomly put in to hopefully coax solver to come up with a different maximum. So keep solution, okay, close. So if you see here, it does the same thing. So it doesn't use this guy at all. It uses your up and coming, it uses studs. And then for everyone else who's roughly equal, it just hires a few of them, all right? Now, one last thing we can try is, let's just see what happens when you provide some more real world applications. Like, sure, this guy's good, but maybe let's just say he's old and his back hurts, so he can only work 32 hours. Similarly with this guy, let's just say this kid's only 18, so he doesn't really, or maybe he's like on a work restriction, so he can only work 24 hours. Let's see what that does to the problem then. So here we have only 1,000 now. It's not as high, which makes sense because your most productive people can't be on the floor as much. So what I expect is a more spread out work schedule, as well as less work for these 2 studs because that's the conditions. And that's what we see here. So if we look at this here, this is color coded by the number of hours. Because this person can only work 32 and 24 now, rightfully so, they're limited, okay? And so who picks up the slack? They just make more people work. So funny enough, they are still willing to, oh, nope, this makes sense conceptually. So they just bring in other workers to start working. And even though he's available because he's so inefficient, they still won't call him. So this would be the solution for something like this, most likely. Both models seem to get to the same number rather quickly. And then one of the takeaways here is that on top of, okay, well, this is my ideal schedule for these conditions, you can also then go down the path of like, well, hey, should we even keep this guy if in no world we see a value to him to the work schedule? So that is how you use solver to optimize a, this is a bad copy and paste, but say like a worker scheduling problem. So yeah, hopefully that has been helpful in understanding what linear programming is and the benefits of optimizing problems in everyday life, I suppose.